It's my honor to be invited to make a presentation at this seminar. Thanks for the organizers for the invitation and thanks for audience online. First, let me introduce HiSilicon Optoelectronics Corporation Limited. Our company's history can be divided into three stages. First, from 1999, optical electronics team is a part of Huawei transport product line. Second, from 2012, HiSilicon Optoelectronics was established. Serves Huawei's major product line includes the data center, router and carrier, transmission, access, and wireless. And now, we serve global ICT and the consumer customers. As shown in the figures, our revenue has increased stably in the last few years and achieved 2.54 billion US dollars in the next year. As shown in the figure, we have some functional department, which is product management department, where I came from, and sales and service department, and R&D management department, and client-side PTT and line-side PTT. As we know that the bandwidth driven by data center requirements boost the global data traffic. Global IP traffic increased rapidly with a CAGR of 26% from 2017 to 2022. Data center traffic exceeded the overall growth. The intra-data center traffic is more than 70%. The data center optical transceivers market is expected to reach $6 billion in the 2025. The proportion of direct purchased by optical modules keeps increasing. 70% are from top 5 OTT companies. They are Google, Amazon, Microsoft, Facebook, and Alibaba from China. A 100 gig Ethernet is a big player in the market in the past 5 years. The left figures show that sales of 100 gig Ethernet module by market segment, and the right side shows the 100 gig Ethernet module by sales by range. Since 2017, cloud have become major market for the Ethernet module. From the perspective of distance, the largest cloud optics market is 500 meters to 2 kilometers. Let's talk about the 400 gig Ethernet. The overview of 400 gig Ethernet standard is covered from 100 meters to the 80 kilometers. IEEE 802.3 working group established the 400 gig standard in 2013. And in the 2015, 200 gig specification was included in the standard. On December 6, 2017, the IEEE 802.3bs 400 gig Ethernet standard was approved. We can see that from the 100 meter to the 80 kilometers, they are full covered in the standard, and we make the 200 gig SR4 and FR4 standard in the same time. 400 gig and 200 gig modules are now available on the market. The next Ethernet standard, the next stage is 800 gig and 1.6 terabit Ethernet. Several groups have started work on 800 gig optical port. First, the APEC. It is established in the September 2020, committed to establish the open, transparent optical electronics standards and optoelectronics industry platform. IEEE beyond the 800 gig established in November 2019, focused on less than 80 kilometers Ethernet solution. 800 gig pluggable MSA established in September 2019, focused on optical for 100 meter to 2 kilometers 800 gig Ethernet. It's about 8 by 100 gig and 4 by 200 gig. QSFP double density 800 gig MSA established in September 2019, focused on modifying and extending QSFP double density to handle 800 G, support 8 lanes of 112 Gbps at the chip-to-module interface. OIF the 800 G ZR and ZR minus pre-discussion. 800 ZR or shorter distance ZR minus initiated by the end of the 2020. As the technical challenges of 800 G and the 1.6 Tera Ethernet increased, technical solutions are standards and further redefined. Maybe the standard will be defined in about 2025. Then I will talk about some challenge in the optical component. The first challenge of 46 gigabaud rate VCSEL is 100 G per lane for 100 meters is called SR. We know that the full wafer processing, the high chip manufacturing efficiency, the laser and the fiber are easily coupled, and the component package is simple. The output optical power is low, and the mode field area is large as a result. Multiple transverse modes are involved, and the transmission distance is limited. We note that Finisher talk about their 400 G SR4 solution. However, the transmission distance is shortened to 50 meters instead of 100 meters. Some customers, such as Alibaba, may be willing to shorten their application scenario to adapt the 400 G SR4 50 meters for the cost consideration. For some customers, such as Google, choose the single-mode solution to replace the multi-mode solution in the 100 meters SR scenario. In the past few years, Chinese OTTs have preferred the multi-mode solution over US OTTs due to cost consideration. The next challenge of 46 gigabaud rate DML is 100 G per lane for 2 kilometers. That is called FR. The spectral fabrication is simple and no docking is required. The chip size is small, which can be used for both laser and modulation. The light emitting spot is elliptical and needs to be coupled with a lens. For direct modulation, trimming occurs when it decelerates the transmission performance, typically used on 10 G and 25 G system. We noticed that some advanced DML vendors in the market, such as Oclaro, was testing 100 giga PBS PAM4 transmission in the lab and require third-party drivers. The 56 gigabaud rate EML has moved to the ODSP direct drive solutions. Therefore, I'm interested in the comparison with the DML driver plus 56 DML chip and the 56 gigabyte rate EML in terms of transmission performance, cost, and power consumption. The next challenge of 112 gigabaud rate EML is 200 G per lane for 2 kilometers. There are some papers on 112 gigabaud rate EML in academia, but no sample yet have been seen yet. 200 G per lane optical are recommended to adapt to the 200 PAM4 series. For 100 PAM4 series is not necessary. Now the challenge of AMDD PAM4 direct detect, MPI, and the dispersion penalty. The table shows the MPI penalty and the dispersion penalty. The 112 PAM4 is used over 10 kilometers and cannot meet transmission requires based on CWDM4 and KP4. 224 giga PAM4 based on CWDM4 and KP4 cannot meet transmission requirements. The stronger FEC needs to be replaced to solve the interconnection problems and increase the latency of the data center switching network. MPI brings challenge to the long-term stability of telecom metro networks. The challenge of server to TOI is copper or fiber. In the past few years, the server to TOI solution choice for OTTs in North America and OTT in China have been generally different. North American OTT prefer DEX, a copper, where China OTT prefer AOC fiber solutions. This has changed recently. The transmission distance of 46 gig PAM4 DEX is less than 3 meters. Some OTTs in China want to use ACC cable. In China, ACC cable will be used in small batches from 2021 to 2022. In the future, 112 PAM4 China OTT generally believes that ACC AEC cables are better than CPU cables. At the time, the DEC capability may be less than 1 meters. The challenge of form factor, the CPO, or pluggable. Let's talk about the electrical SerDes. 112G SerDes in the IEEE 8023CK, 100 per electrical line backplanes, chip to module, and copper cable. OAF CEI 112 gigabit MCM XSR VSR membrane area study, and 224 giga SerDes is expected to be available in the 2 or 3 years. The pluggable modules are widely used, which is a bit obvious. The 112 gig SerDes solution is mainly pluggable. The 224 gig SerDes may be OBO or co-package and may have some opportunity. Okay, let's go to the challenge of long haul. Its larger capacity and higher performance. WDM involves in the 3 dimensions: high baud rate, wider spectral width, and high density form factor. 400 gig coherent optical module component requires 45 gig baud rate, and the long haul requires over 100 gig baud rate. To achieve 800 gig coherent transmissions, the baud rate of the optical component must be higher than 90 gigabit. Wavelengths extend from the C band to the C+ band, then to the L band. And the module package continues to evolve to minimize and low power consumption from MSA to CFP and the CFP2 and the QSFP. The challenge to the size and power consumption of components and chips. The challenge of high baud rate. High baud rate benefits first effective bandwidth compared with the 96 gig baud rate and the 32 gig baud rate. They are 0.7 dB gain. And the first is per bit cost and per bit power consumption. Give you an example comparison. Compare with 32 gig baud rate and 64 gig baud rate. Per bit cost reduced 15 to 13.5%, and the per bit power reduced over 50%. According to the recent public reports, 800 gig coherent system based on 90 gig baud rate can be commercially used. And the high baud rate challenge optical, electrical chip implementation capability, component implementing cost. And we still need the 800 gig and the 1.6 terabit coherent long haul solutions. The challenge of 800 gig and 1.6 terabits on 2 kilometers. There are two solutions: is MDD and coherent. As we show that in the 800 gig, coherent still haven't enough advantage. We show the 800 coherent and of 8 by 100 gig PAM4 and 4 by 200 gig PAM4. We can see that the 800 gig coherent seems not attractive in the data center. 800 gig coherent may be used in the 10 kilometer and above. In the 1.6 terabit, is a big chance for coherent used in data center. This figure shows the CD limited reach of PAM4 transmission. We can see that in the 200 gig Gbps PAM4, the reach limited is about 1.5 kilometers, and the CWDM8 is a 200 gig Gbps PAM4 is reduced to 750 meters. So coherence may be needed to build 1.6 terabit Ethernet 2 kilometer solutions. Okay, let's get to the summary. Optical networks have multiple applications. The performance, cost, and the power consumption of optical modules need to be jointly optimized based on different requirements. Short-reach datacom use the optical chip platform with optical cost based on scenario and application. MDD technology, cost and power consumption first, and the performance is enough. The different optical chips such as VCSEL, DML, EML, silicon photonic platforms based on application needs. And in the long haul, the WDM performance first. The challenge is improving capacity. WDM network, the coherent technology, performance first, and the compatible power consumption and cost. Currently, single wavelength 200 gig and 400 gig is supported. In the future, long haul, the 800 gig solution need to be considered. So that's all. Thank you.
Thank you very, very much, Yibo Liang, for a great presentation. Thank you for this fantastic overview from 56 gigabit per second all the way to 224 gigabit per second VCSELs and any other component on silicon photonics. And one thing, Yibo Liang, that we'll be discussing already with our members is that the next step to go to 1.6 tera after 800G is going to be driven by a 200 gigabaud channel. And that's something that, in my opinion, is a big paradigm shift. We are going to have to multiplex higher capacity channels. My question here is, what are the main challenges, in your opinion, to enable a 200 gigabaud channel?
Okay, your question is what's the main challenge for the 200 gig get baud rate, right?
Yes.
I think in the 200 gig solutions, there are two major challenges. First is on the electrical side, that is 200 gig SerDes. As we know that the SerDes, the drivability will limited in the over 100 gig is a big challenge for the SerDes. And another is for the optical side. As we know that the 200 gig should first be maybe used the EML. EML can be the more higher bandwidth. But we have seen some paper on it, but not sample. But I think the optical side may be solved in the 2 or 3 years. Since is a little difficult in the electrical side. Maybe some another alternative technologies such as the CPO or OBO or some optical I/O may be used in the 200 gig.
In your presentation, you also talk about the transition towards 1.6 tera, and I was very happy that you said that 800G, we didn't see enough advantage for coherent. 1.6 tera is the big advantage for the coherent detection. Do we have technologies already for the balanced photodiode that we need in a coherent transceiver at that ultra high speed?
Okay, I think if the directly detected technology can achieve the requirements of the data center, the coherent have no opportunity because they have a high power consumption and a high cost, right? So I think the opportunity for the coherent is 800 gig, 10 kilometers, and 1.6 terabit Ethernet on the 2 kilometers. But I think the coherent technology to down into the data center, it should be simplify their complex. They will know some either in their FEC and another angle noise to reduce their power consumption and their gate of the CMOS circuit.
I have a question. By the way, thank you very much. You've been fantastic, Yibo Liang. I have a question in the room coming from a company in Canada called Aeponics. And Aeponics is great because they mix silicon nitride and MEMS in their platform, a fantastic partner. Francois Menard, who is the founder of Aeponics, he's asking, we seem to see a trend to have fast DMLs because they consume less power for the drivers. Do you really think EMLs are the way to go?
Compared with the EML, DML, and the VCSELs, the bandwidth of EML is high, and the rate limited of EML is high. I think this will be a good solution for the data centers, and because the VCSEL may be in the 56 gigabaud rate, the range will be limited on the 40 meters, and the DML, I think the 56 gigabaud rate, the DML can achieve 2 kilometers, but they need a third-party driver, and we know that the EML can be driven by the CMOS driver can be integrated with the PAM4 DSP. I think in the future maybe the DSP with a low voltage EML is a good solution.
I fully 100% agree. The future is direct modulation with the seamless integration with electronics. Yibo Liang, thank you very much, CSCA, for being with us today. It was truly great to open Photonics Plus with a keynote presentation from HiSilicon. Thank you so much.
Okay, thank you so much, and thank you for the audience online.